folks, and welcome to this lesson on standard reduction potentials. By the end of this lesson, you should be able to use standard reduction potential tables to find the potential of a half reaction, and use standard reduction potential values to find the overall potential of a redox reaction. Now, when it comes to various different types of chemical reactions, there are a lot of different values that are relevant to them. Some of them are energy, and that information can be very useful, and this is one of those ones. So since we're looking at standard reduction potentials, the value that we're going to be looking at in this case is potential. And when I talk about potential in this case, we're talking about potential energy and the potential energy difference. The symbol that we're going to use for these standard reduction potentials is capital E, and the unit is going to be volts. Now, to explain this whole concept, we're going to go for the good old waterfall analogy, where your electrons can have potential energy, and they can take that energy and use it towards something else. So if the electron is going down a waterfall, it can release energy to be used for something else like heat, or electricity, or so on and so forth. And if the electron has to go up the waterfall, then it needs to absorb energy from something else to be able to go up that waterfall. This whole releasing energy or needs to gain energy idea is expressed through the signs of the values themselves. So if you see a positive E0 value, your electron is going downhill, and so it is releasing energy. And if you see a negative value, it is going uphill, and so it needs to absorb energy. In terms of spontaneity, so in terms of a reaction happening as it is without needing to put energy into it or anything like that, you want those positive values are going to be what are spontaneous. Now, when it comes to energy, you can't really have exact absolute values for them. In other units that you have seen or will see in the future, energy is always going to be a comparison to something else. So it might be the before and after, what is happening there. The values that you see for these standard reduction potentials are going to be comparisons to a specific reaction, which we will see in the next slide. So we've talked about the potential part of standard reduction potential. Let's talk about the two other bit. So when you are seeing tables of reference for these values, you are going to see that all of these reactions are written as reduction reactions. This is so that it is easy to use these values for what you need to use them as. These values are also sort of stoichiometric, but not quite. So the thing is that when you have your reduction reaction, and what's happening in the reaction that you're interested in is that this half reaction is not reduction, but it's oxidation, you can flip the reaction, and the sign for that E0 value is going to flip. However, if you need to multiply that half reaction by, say, 2, to get the proper final balanced redox reaction, you're not going to multiply that E0 value by 2. If we're going to use a waterfall analogy for why we don't multiply these values by 2, it's because the electrons are still traveling that same height, you just have more of them. And so the distance or the difference between where it's starting and where it's going to isn't any different. The standard part of standard reduction potential means standard conditions. So that means we're dealing with 100 kilopascals and 298 kelvins. Now, because of the fact that we are dealing with a lot of solutions, and the solution concentrations actually do make a difference, the standard concentration that we're looking at is also going to be 1 molar. If any of these change, so if the temperature or the pressure or the concentration of the solutions that you're using change, we can't use the E0 values that you're given anymore. Now, I did mention the fact that these standard reduction potentials those values are a comparison to something else, and that comparison is made to the standard hydrogen electrode, or the SHE. So in this particular case, this electrode is made from the half reaction between hydrogen ions and a hydrogen gas. So you can see the equation at the bottom. It is H plus aqueous, it is 1 molar, and then you're making the gas, and the gas is going to be at 100 kilopascals. The value, the standard reduction potential value for this is 0. So every other half reaction is going to be a higher value than this or a lower value than this. So generally, all of those standard reduction potential references that you see are going to look something along these lines. You are going to see that all of them are written as reduction. You're going to see the values on the side. So here's that not that I keep on talking about. Not refers to the standard. And so anytime you see any kind of not value, it just means that it's in standard conditions. Generally, every single table of this sort that you're going to see is going to have the most negative values. They'll get less and less negative until they get to that standard hydrogen electrode, which has that value of 0, and then you're going to get more and more positive values as the list keeps on going on. You're also going to find that all of these reactions are written so that you have 1 mole of your oxidized species. All of the other numbers can look a little bit funky because it's based off of 1 mole of that oxidized species. So you can see that there is a difference in the number of electrons for each of these. Sometimes you're going to get fractions on the other side of the equation, but yes, it's based on the fact that you have 1 mole of that oxidized species. So let's look at an example of how you can use these values. So here we have find the overall E0 value for the redox reaction between magnesium and copper 1 ions under standard conditions. So a reaction is going to happen between magnesium and copper. We're looking at a redox reaction, so this magnesium is probably going to become an ion, and so this copper is going to be displaced and become the solid copper. So let's look at the reduction potentials that we can be looking at. So we are looking at the oxidation of magnesium, and we're going to be looking at the reduction of copper. So the two relevant the two relevant entries on that table are going to be these two. Now the copper itself is going to be reduced, and so this equation as it is works fine for what is going to happen in that redox reaction as a whole. In terms of the magnesium, however, we need to reverse that reaction because magnesium is going to be oxidized. So our magnesium is going to go from this to here. And if we look at our E0 values, this is going to be flipped. So instead of negative 2.37, it's going to be positive 2.37. Now for that copper, it's as written, so it's still be a reduction reaction, so our E0 is going to stay as it is. Now to have the full balanced redox reaction, we are going to need to take this reaction and multiply by 2, but remember, we're not actually going to multiply this value by 2. So to combine these half reactions, you're going to add everything together. Those electrons are going to get cancelled out so they don't show up in your final balanced equation. And for the E value for this entire reaction, you simply add these E0 values for the reactions as they are written. And so in this particular case, this value is going to end up being 2.89 volts. So that's the end of this lesson. I'll see you next time.